So for our next discussion, we're going to be looking at some questions that actually come from your textbook, starting with 598. So if you can't see the word on the screen, if you'd like to follow along there later on, or even right now, you are certainly more than welcome to do so. So here is our situation. We are looking at a store that's having a sale, and the sale is a 20% off sale. And that's often how they go. Rather than setting a certain dollar amount that prices go down, they put a percentage. So cheaper items, 20% off a dollar is 20 cents. But 20% off of $10 is $2. So the more expensive something is, the larger the dollar amount that you save. So it incentivizes people to maybe buy more expensive things. So we're looking where we have a 20% off sale. So Trixie is going to buy some shirts. And there's also sales tax. You've encountered sales tax, right? So if something costs $1 and you got a 5% sales tax, you actually get charged $1.05 because of that sales tax percent increase. Now, the question here is, so Trixie sees that the clerk put the sales tax on first, making the overall cost go up, then took the 20% sale discount off. And Trixie wonders, hey, does that make a difference? And if it does make a difference, does doing it in the other way help me more or help me less? So what I'd like you to do here is really do take a moment, think about A, does it make a difference? And B, if it does, which direction do you think would be more helpful? So you make your educated guess. I'm going to say it this way. State your hypothesis. Hypothesis, of course, the very fancy word for an educated guess. So make your estimate. Now, let's do an investigation. So we're going to imagine this, and there's a little visual setup here. So there's two grids. In both cases, there are 100 squares. So it's 10 across, 10 up and down. So 100 squares in each grid. These are going to represent the cost of a $100 purchase. And we're going to apply two discounts, but we're going to do it in two different orders and see if changing that order makes a difference. So we got Karen. She works in a store and gets a 20% discount. That's often true. If you work at a store, you get what's called an employee discount. So in this case, we're looking at a 20%. Now the store is also having a sale, meaning that everything in this sale is 30% off. That's actually a big amount, the 30% off. So you don't see sales that big very often. So Karen's going to buy this $100 dress. She's going to use both discounts. How much does she pay? And does it matter which one comes first? Okay. Now here's the thing. When you are doing these discounts, you don't just take 20 plus 30 and call it 50%. It doesn't work that way. Instead, what you do is you take one percentage, see how much money is left, then take the second percentage to see what your overall final price is going to be. And very often that works out to being less than if you added the percentages together. So let's see what happens in this case. So use the first grid to represent the 20% discount first. Okay, so right now this is the full price, $100. Let's figure out how much that 20% discount is going to be. So 20% of 100. So we know of means multiply. 20% is 0.2. 0.2 times 100 is $20. So I'm going to now cross off here 20 squares representing the $20 that we have already discounted. And I'm going to make those red to show that this matches her employee discount. Okay. So already the price went down from $100 to $80. Now for the follow-up. Now what we have left is an $80 price, and we've got this second discount, this 30% discount. So we want to see how much is going to come off this time. So turn that into a decimal, that's 0.3. Multiply that by 80 this time, and you should end up with 24. So let's cross off another $24 here. I'm going to do this in blue this time. So there's 10, 20, 1, 2, 3, 4, 24. So the red was the employee discount. The blue here is going to be the clearance discount. And what's left, so the squares that aren't crossed out, that's how much he's got to pay. So we've got 10, 20, 30, 40, 50, 1, 2, 3, 4, 5, 6. Okay. So the overall price was 56. So we actually are answering part of the next question. So in case one, how many squares were left? There were 56, which means the price of the dress after those discounts is $56. Now let's see, does it make a difference? If we do the discounts in reverse order, do we end up with a different price? Let's see if your hypothesis ends up being correct. So this time, we're going to do the 30% discount first. That's off the full $100 price. So turn that 30% into a decimal. Of means multiply. So this ends up being, $30. So right away, it looks like we're a little bit ahead. Let's see how things turn out. So 10, 20, 30. So notice that the 30% discount, it was bigger this time. I want you to think about why that is. Okay, so that leaves us with $70 remaining. So now her 20% discount is applied, her employee discount is applied to that $70. Well, 20% of 70, move the decimal over 2 spots, that's 0.2 times 70, which ends up being 14. Notice that's a little less this time than it was in the first case. But we're going to cross off now another 14 boxes. So there's 10, and then 1, 2, 3, 4. Make them red to show that they are the employee discount. Okay, so even though the distribution of the red and the blue is different, I hope you can see that in both cases, 10, 20, 30, 40, 56, there's 56 boxes left. So in case 2, there were 56 boxes, meaning, you know what? I actually answered the wrong question here, but we talked about that already. We talked about this already. So in both cases, we end up with a $56 overall price. So here's what we're seeing. Discount 1 and 2 in either order got us the same price in the end. So first off, does that match up with what your educated guess was? And secondly, let's now think about why this makes sense. If we take a price, and I don't know what price it's going to be right now, I'm just going to call it X. Let's think about what it means to decrease by 30%. Well, from our previous discussion, we know that means I'm going to take 100% minus 30%, which is 1 minus 0.3, which is 0.7. So to decrease something by 30% means to multiply by 0.7. Okay, what does it mean to decrease something by 20%? Okay, well, 100% minus 20% would mean that to decrease a number by 20%, you multiply that number times 0.8. Now here's the thing. What if you do both of them? So what if I want to take my X, and if I want to decrease it by 30%, and then decrease it by 20%? We'll multiply those together, and you're going to end up with 0.56 times your X. What if we do the exact same thing, but in a different order? What if I take my X and do the 20% discount first, and then the 30% discount? Well, the order in which you multiply doesn't make any difference. You're going to end up in the exact same spot. So that's how I like to think about it. Percentage increase and decrease. If you do several of them in a row, because it's all multiplying, the order of multiplication doesn't make a difference. You're going to end up in the same spot every time. So that's why I would say these results make sense. That's how we ended up with that $56 dress both times. So back to here now. So looking at the Trixie that we started with that made us make this educated guess. So if her shirts cost X dollars, we've got two things to take into account. A 5% sales tax, which would be an increase. And then I want to double check 20% sale, which would be a decrease in the price. So if X represents the cost, how could we represent the tax? When you're representing things, please start with words. It just makes it so much easier. 5% of the cost. So 5% of X. We know of means multiply. We know 5% as a decimal is 0.05. So 0.05X. That's how I represent the tax. How could you represent the cost plus the tax? Okay, well, the cost plus the tax. The cost was X. The tax was 0.05X. Add them up. Remember that imaginary 1, 1.05X. I hope this doesn't come as a surprise. We've talked several times now about how when you increase something by a percent, you add on that percent as a decimal and turn it into a multiplier, just like that. So there's just the tax. Here's the cost plus the tax. So let's do a double underline on this, and a single underline on that. How could we represent the discount and the cost of the shirt after the discount? Okay, this is going to be very similar. So the discount was 20%. Okay, so make that 0.2 times the cost, right? 20% is 0.2, of means multiply, the original cost. So there, that is the discount. There's the discount. Now, cost of shirt after the discount. Cost minus discount, since the cost is going down. Imaginary 1 minus 0.2 is 0.8. There that is. And this, again, shouldn't be a surprise. This is how we would figure the multiplier, right? 1 minus 0.2 is 1 minus 20%. 0.8 is what's left behind. So did Trixie get charged more because the clerk added the tax first? This goes back now to that same question. Adding the tax first would mean take your price, multiply by the 1.05, then take the discount, multiply by the 0.8. I'm going to use my calculator here. 5 times 0.8 means that the overall final cost, 0.84 times the cost of the shirts to start with. What if we did the calculations in the reverse order? So if we took the original cost, decreased the price, and then added the tax on. Well, it's the same calculation, right? Order of multiplication doesn't matter, so we end up in the exact same spot. So did Trixie get charged more? No. When it comes to adding a tax and providing a discount, because they can both be viewed as multipliers, and because the order of multiplying makes no difference, you're going to end up in the same spot, regardless of which order you do things in.